Welcome. This video is going to start looking at problems that you could find in Section 3 of Chapter 1 of the Brown SL Chemistry book. So starting with question number 36, we're going to be looking at percent yield, theoretical yield, limiting reactant, all that good stuff here. So you're given the following equation in 36, and you're asked how many moles of Fe. So I like to write right under my equation what I'm trying to get. Moles of Fe from 1.25 moles of Fe2O3. So this one's pretty easy. All I need to do is go ahead and take my 1.25 moles of Fe2O3, set up a molar ratio, and I see I should expect 2 moles of Fe from 1 mole of Fe2O3. And I don't care if you're this meticulous about your labeling, I'm just doing it so those of you trying to follow my work can. But I would expect 2.5 moles of Fe from 1.25 moles of the Fe2O3. So then B wants to know how many moles of H2 are needed. So I'm going to switch over to red here. Moles of H2 needed to make 3.75 moles of Fe. So now when I set my ratio, I have 3.75 moles of Fe. It doesn't matter that we're comparing two products here. That's the beautiful thing about balanced equation. You could compare products to products, reactants to reactants, or reactants to products. And I want moles of H2O. So moles of H2O should be the top of my conversion factor, and moles of Fe could be the bottom. So this could be a 3-to-2 conversion factor. So when I multiply that, I'm going to get 5.63 moles of H2O would be needed to make 3.75 moles of Fe. And then finally, C says, if the reaction yields 12.5 moles of H2O, so I'll go to my final color here, 12.5 moles of, oops, that was the H2O though. What mass of Fe2O3 was used up? Now this time I'm being asked to switch it to grams. So go ahead and write down what I was given, 12.5 moles of H2O. I know I want to find out about the Fe2O3, so I might as well convert this to moles of Fe2O3. So that's the only way you can communicate in chemistry. So moles of H2O, and I see that that's a 1-to-3 ratio. So 12.5 divided by 3, give me a little more than 4.16, 4.17 moles of the Fe2O3. And now if I want to convert that to grams, I have to find the molar mass of Fe2O3, which I find to be 159.7 grams. So then when I multiply that by the 4.16, I'm going to get, keeping 3 sig figs, I'll get 665 grams of my Fe2O3. So number 37, you're being told about butane being combusted, and you're given the formula for butane of C4H10. Just make sure you know that's an H there. And so if you combust it with O2, you'll get CO2 plus H2O. And when you balance, I balance with a 4 here, which means I need a 5 here. And this is one where I'm going to end up then needing 7.5 moles of oxygen. So instead I'm going to double this to 2, 13, change this to 8, and double this to 10. So if I just rewrite that, 2C4H10 plus 13O2 will yield 8 CO2 and 10 H2O. So that was question A. And then B wants to know what mass of butane needs to be burned if 2.46 grams of water is recovered. So I need to know how many moles of water that is so I can predict my moles of C4H10 and then convert that to grams. So 2.46 grams of water divided by the molar mass of 18.02 is going to give me 0.1365 moles of H2O, My equation lets me know I get 2 moles of C4H10 for every 10 moles of H2O. So I'm going to divide that by 5, and I'm going to have just 0.0273 moles of butane. The molar mass for butane then, I have my 4 carbon plus my 10 oxygen. So I've got a molar mass of 58.14, and when I multiply that by the 0.0273 moles, I'm coming up with 1.59 grams of butane that would be burned. Question 38 gives you this rather lengthy equation, and really all you need are the 2 reactants, because it says how much NH4ClO4, so that's ammonium chlorate, would there be to completely burn every kilogram of aluminum. So the first thing is you need to realize this is 1,000 grams of aluminum, and then I'm going to have to convert that to moles of aluminum so I could predict my moles of NH4ClO4, and then convert that to grams. So 1,000 grams of aluminum, 1 mole of aluminum weighs 26.98. So 1,000 grams is 37.06 moles of aluminum. And I see it's in a 3-to-3 ratio. So that means my moles of NH4ClO4 and my moles of aluminum really are the same. So I'm really working with 37.06 moles of NH4ClO4. So now I just need to find the molar mass of ammonium perchlorate. And when I do that, I come up with a molar mass of 118 grams per mole. And so when I take that times the 3706, I come up with 4374 grams, or 4.4 kilograms. So question number 39 gives you some information, and this is a common problem for chemists, that you have limestone or some other rock, some other mineral that is mostly what you want, in this case calcium carbonate, but not 100%. So you have a 1.605 gram sample, and you want to know what percent actually is calcium carbonate. Well, when you heat up that 1.605 gram sample, we know it decomposes into calcium oxide and CO2, and 0.657 grams of CO2 is collected. So I can work backwards, changing this into moles, using that to calculate my moles of CaCO3, and then my grams of CaCO3, and then finally I can make the comparison with the limestone I was given to begin with. So when I do that, the 0.657 grams of CO2 has a molar mass of 44.01. So 0.657 grams is not very much. So we're talking about 0.01493 moles of CO2. And since this equation is all 1-to-1, as we showed in part A when we wrote the equation, assuming everyone did that without a problem, this is also then how many moles of calcium carbonate I have. So then if I find the molar mass of calcium carbonate, I get 100.09. Go ahead and multiply that by the 0.01493, and I'm coming up with 1.494 grams. And so now if I set my percentage, 1.494 out of the 1.605 times 100% means we're looking at 93.1% calcium oxide. So then part C wants to know, what assumptions are you making? Well, you're assuming that the only source of CO2 that's being produced here is from the calcium carbonate, that there's nothing else than limestone releasing CO3. You're assuming that the CaCO3 completely decomposes and gives up all of its CO2, and that all the CO2 is being captured. So several assumptions being made as we do this experiment.